would like to introduce our next speaker, who will be speaking on strategies for enhancing fire performance of concrete structures incorporating fiber and fused polymers by Venkatesh Kodur. He is a University Distinguished Professor at Michigan State University, is an internationally recognized scholar in civil and fire engineering. His pioneering research has led to innovative design solutions for fire performance in materials and structures, influencing global construction standards. Elected as a fellow in 7 prestigious institutes and academies, including ACI, he has received numerous awards. Dr. Kodur notably contributed to the investigation of the World Trade Center's collapse after 9/11 as a part of FEMA, Federal Emergency Management Agency, and ASCE expert team. So let's call on for his presentation.
So basically, in today's presentation, I'm going to talk about what strategies we can implement for enhancing the fire performance of concrete structures incorporating FRP. Okay, I'm very much thankful for NEXT ACI for organizing this and to be part of this workshop. First, I will quickly give some background information about emerging trends in the construction sector and why FRPs may be a best possible solution in the current environment, as well as what are the problems, especially fire problems with FRP. Then I'm going to present, based on some of the work we did as well as others did, on fire resistance studies on FRP, strengthened FRP incorporated structures, discuss some of the critical parameters, and then finally present quickly some of the innovative strategies which are already available that can be implemented. Now, as we all know, here we are all experts in FRP as well as in the construction sector. The deteriorating infrastructure is the worldwide problem, right? Especially with respect to reinforced concrete and steel structures, corrosion is a major problem in concrete as well as the steel structures. And then we have this problem of age-related issues with concrete as well as steel. The second thing is, as our lifestyles are improving, as the world is finding out more research and development in most countries to enhance the performance of the structures which were built in 50s and 60s and 70s, 80s, the performance is being upgraded to account for higher earthquakes, blasts, impact, and other loading types. Also in the emerging world especially, the number of buildings, there was a 6-story building. Now in an airport, they want to add another 4 stories because there is no other space, so they want to strengthen those structures for enhanced capacity. This is becoming common. US to a lesser extent, but outside because of the land values and stuff. According to health report of US infrastructure by ASCE report, this problem is huge, even in the US. They estimate $3.6 trillion will be spent on this in the next 10 years, right? So, the construction industry is basically looking for solutions toward this. New generations of concrete are coming, as well as new types of, especially non-metallic reinforcement, which is not corrosive or which won't lead to deterioration quickly, as well as unique techniques as well. That's where ACI committees such as 440 are publishing a lot of documents which are of much use. Now, FRPs are a feasible and attractive solution for this. Why? In terms of application, it can be used internally or externally. Internally, you can replace it as a primary reinforcement, as Steve showed us to some extent, right? Either pre-stressing is quite possible. And externally, you can add just small like credit card chips, credit card type of plates. You can add underneath a bridge for flexural strengthening or shear strengthening, and the sides you can add externally bonded reinforcement, or much more attractive is near surface reinforcement, where you can cut through this and put your bars or strands and then fill this with epoxy or with concrete or whatever. That can be done. Now this offers either internal reinforcement or external reinforcement, which we have 2 types. Now, in all this, FRP has number of advantages. I don't want to get into this, right? High strength, lightweight, ease of application, number of things. But in terms of the disadvantages, there are disadvantages as well. Like it's brittle, bond is an issue, major issue. Then, because the bond in the externally bonded one, you get only one side bond, unlike inside when you insert where you get 3 or 4 sides, as well as, FRP is a combustible material. Fire can be an issue, especially when it is directly exposed to fire, as in the case of EB, externally bonded reinforcement. But having said all this, it's a much better option than what we used to use as steel plates using this, which are heavy, right? And as well as even installations is a big problem. So this is a better solution. But we need to address fire problem. Why? Fire represents a severe hazard and threat to the built environment. It causes thousands of deaths and billions of dollars of damage each and every year in each and every country around. Right? Unlike, for example, earthquakes, which happens only in the West Coast mostly. Unlike tornadoes, which is only in the Midwest. Unlike hurricanes, which are mostly in the East Coast or the South. Unless the snow, which is only in northern part like Michigan or, Wisconsin. But fire is a universal problem. From a small village in Minsk, Russia to Chile, Santiago, fire is a significant hazard to the built environment. Now, if you see the statistics, there was more than 1.35 million fires, leading to, out of which 486,000 fires were called structural fires. They grow into the full extent where they can do some level of damage to the structures itself, right? Now, total losses was more than $50 billion in addition to 3,800 deaths. This was in 2021. So when it happens, fire represents a severe hazard, not only for people, but also for the structure as well as the environment, right? It's one of the worst conditions faced by the structure during its lifetime. It can happen through an electric short circuit, as simple as an electric short circuit, accidental. Or intentionally, vandalism can happen. Or, after an earthquake, a lot of times you have fire. Look at Kobe earthquake, San Francisco earthquake in 1906, Northridge earthquake, also there were some New Zealand earthquake, Chile earthquake, post-earthquake. Fires are common. After a truck hits a bridge, the bridge is designed for that impact load, but not for the fire following it. That's why the bridges, fire becoming a big problem, right? Or an impact loading. 9/11, for example, I was part of the investigation. 40 buildings suffered major structural damage or collapsed in 9/11 incidents, not just 2 towers. Many of them were not hit by the planes. So fire is a severe hazard and threat. And we do a lot of things. As a secondary event, it's a problem, or as a primary event. We put in a lot of sprinklers. Steve talked a lot about this. Active fire protection systems such as sprinklers, heat detectors, smoke detectors, exit paths. Then we also put in passive fire protection measures. That means without any sensors it works. That is basically our fire resistance, how long a structure can stand up without coming down. Basically as simple as that. That's fire resistance. And it's very important, especially not only from the resiliency point of view, life safety point of view also, it's very important. Higher the fire resistance, higher the resiliency of the structures. I don't want to get into too much into this. Fires are real. And it's happening as we speak. A lot of times we assume that fire is a rare event, only it happened in 9/11, after that, No, every year there are fires happening as we talk or as we speak right now. This is one example is this is a New York City Bronx on 6 January 2022 in an apartment building. They were residents, it's mostly immigrant community. In fact, language was an issue as well. They were warming themselves up with a spot heater, block heater, because fire affects poorer sections of the society much more than rich and affordable sections, weaker sections of the society. Whether it's elderly people, whether it's women, whether it's pregnant women, whoever, a weaker section of the society, because of their lifestyles, because of the expensive nature of having the fire protection systems as well. So in this case, they were warming themselves, kids were playing, it goes out of control, exit paths were not working, number of things were not working. 8 children plus 19 deaths, right? 3 days before that, same thing repeated in Philadelphia. Same thing, 18 people died. So this keeps happening, and it's not just buildings alone. I don't want to get into each one of them. You all know what happened on I-95 bridge, Philadelphia, you know. So in this bridge, basically, it was a steel girder bridge, but there was concrete decking on the top. Oil tanker, 8,500 gallons of fuel flipped on its side. Huge fire starts. Fire department comes in quickly, but still no way the girders can withstand the fire, and spans collapse. And it took weeks to get their supply chain issues. Remember, in bridge fires, life safety may be of lesser importance. People don't die that much, right? But what happens is the property damage, and following that, and these days, you know, it's all traffic. Everyone, we live most of the time on the road rather than in houses. So that's why, as Steve said, there is a rethought on these regulations. Now, it's not just one type of incident. As you see, what happened? I-85 bridge outside of Atlanta Airport on I-85 highway, right? This bridge was in very good condition, reinforced concrete piers, pre-stressed concrete girders. They inspected it in 2015. They found everything, bridge received a good rating. But they found out there were drainage issues. To fix that, they bring in PVC pipes, and I don't know whether you can see that there or not. So they assembled all of them. And in US, our construction season starts in May. So they went away after putting the pipes in February. Homeless person comes in. This was based on the investigation. So he wants to, it was a very cold day in Atlanta. He was warming himself up. He put some rubble and he started a fire to warm himself up, all the papers and so. Then he was drinking as well. They found beer bottles right next to him after the, you know, when the investigation done. Then it spreads to the fire. Huge fire starts. Somebody calls the fire department. It's a major highway. Then, when the fire department came in, they couldn't fight the fires. Now you know what spalling is. Steve showed in those girders, right? Now you can see here, huge spalling. They couldn't. It was hitting them like bullets. You know, it's these fragments which comes out. It's called mini explosions. So they couldn't fight the fire. Spans collapsed. It took weeks or months together to fix it. Now, what's the difference when you put FRP into this concrete, either internally or externally? As you see, you are dealing with smaller cross-section. FRP has very good strength properties at room temperature you design, so you are dealing with smaller cross-section. It's a combustible material, unlike your concrete and steel. FRP adds fuel to the fire, which you need to account for. Then, what are the, you don't have to provide too much cover, right? All our, as pointed out, all our fire resistance is based on how much cover you provide based on the current codes. You don't need that cover. You know why? Because it's not non-corrosive. So that corrosiveness, because of that we put cover that supplements the fire protection as well. Then it's directly exposed to fire like EV. Before, your reinforcement is directly outside, right? FRP reinforcement, which is secondary reinforcement. Then problem is steel. They have consistent properties across all grades of steel almost. But here, your properties change with glass, carbon, aramid. Each one has its own this thing you are using, right? Matrix as well as the fibers. Then you have much lower critical temperature. Critical temperature is the temperature at which steel is meant for steel. 50% of the strength is lost. I will show you. GFRP, CFRP has much lower. You lose strength much faster than that. Then in added to that, you have performance issues such as bond, even at room temperature, right? And ductility. So all this leads to lower fire resistance in FRP structures. Now, current approach, as I said, I don't have to repeat this too much. We put in to address the fire hazard. It's not that we are inventing today. From Hammurabi Code in Iraq, when they developed the code, they had one line for fire design. If fire happens, if somebody dies, cut off the hands of the engineer. That's it. I mean, that's as simple as that. So fires were prescriptive from a long time. So we have moved on to putting cover thickness from cutting off the hands. That's all we have done. Still, we use the prescriptive approach. So in this case, we put in sprinklers, smoke detectors, exit paths, active systems. Many times these active systems are not 100% reliable. Sorry to say that if there are sprinkler industry and stuff, You cannot depend on them. Then the second option, that's the first line of defense. Second line of defense is what? Firefighting. Firefighting, often, especially in a lot of urban areas, not in the US, I'm talking about across the international scene today, it reaches 2 hours sometimes it takes to reach in the traffic to the firefighting. Response times are slower a lot of times. Firefighting, 100% not guaranteed to fight the fire very quickly. The third option, which is the structural fire safety, which is passive fire protection, is always there. There is no sensor, there is nothing, it's waiting to happen, it's built in, and it's the least expensive option for enhancing the fire performance of a structure compared to active systems. Sprinklers are so expensive, firefighting, cities don't have any money, right, in the current way of doing things. So that's why fire resistance is very important. And this fire resistance depends on a number of things, including how severe your fire is. Right? So for a bridge fire is much different than a building fire. And when you have FRP, your fire scenario changes. In fact, as Steve was pointing it out, we had done a lot of tests over my career. Doing FRP tests, I'm always nervous and I don't want to do the test because it's hard to maintain in the furnace certain temperature. Just like wood, it starts to burn. To control my burners, to put less fuel, it's a big challenge, right? So that's a problem. Then it depends on fire severity. It depends on material properties. We all know FRP properties are much more worse than concrete. Then we have structural properties. Bond, for example, what level of load. When you add FRP, your service load levels go up. Many people don't consider that in their test. They still use whatever you use on the concrete. Remember, once you strengthen it, your capacity goes up, so you have to increase your service load levels as well, for example. Restraint, right, as was pointed out, right, as well as anchorages is an issue. So all this, I have less time for my presentation, so I don't want to repeat this, but you can see here, so all these issues lead to lower fire resistance. One of them, which I think I will use the next couple of slides on this one, is here. Currently there is major knowledge gaps with respect to FRP. There is some available knowledge with respect to, for example, if you see this is what happens in the material itself. Okay? Once it reaches TG, that's the glass transition temperature. It used to be 60 degrees about when we started this work about 15, 20 years ago. Now they have moved on to 80 to 100 degrees or maybe sometimes 110 degrees in the current FRPs. So once it reaches TG, then what happens? The polymer starts decomposing. And at 200 or so, it much more decomposition happens, completely gone. Around 500 degrees, this graph has moved based on fitting all these logos here, so don't pay too much attention. I have some test data I'll show you. But anyways, this is the trend at which the material properties, tensile strength, for example, degrades. Now, there is some tests as well. Limited tests of data is available. But the problem is there are no test standards. So, a lot of them, when they do for research purpose, they do their own way of doing things. So, this is a problem to collect all this data and then come to certain way of seeing, what is what. The next problem is codes and standards. Obviously, ACI 440, the technical note is very useful, what we have in 440, but still, it's not in a standardized form where it can go to IBC, and, that is what is needed for broader use in the field. Now, Euro code, for example, says, if you add FRP, neglect the FRP from file design point of view. That's what Euro code says. Or put some insulation around it. That's not the way we should be doing in 2023. We can engineer the system very well. That's what I'm going to show you. Okay? So, we have carried out over the last 20 years a lot of work for number of industries, government, all organizations, right? And specifically I'm talking about FRP, including 5 companies, Structural Technologies, Tarek is here, right? Master Builders, right? Mitsubishi, right? We collaborated with Queen's University. Professor Mark Green is here over the last 20 years or so. We worked together, developed we did a lot of fire tests. We had unique facilities at both at NRC and more recently at Michigan State University. We have facilities to do these tests. develop material properties. That's where if you want to use engineered methods, you need material properties. If you want to use calculations, then develop some design guidelines after parametric studies and with using numerical models. These are some tests. As I said, it's not just for testing the structural members. Even to test material coupon test, we don't have STM standards at elevated temperature, not at room temperature. It's much more complicated because the grip during the bond test, each thing is a PhD thesis. For example, my students have worked in the bond strength. They have to develop a new test method to address different FRPs, how to get the grip in these materials, right? So, we did many of these tests, both thermal properties and mechanical properties. Just to show you quickly the results, this is for NSM type of CFRP strengths. This is tensile strength versus temperature in degrees centigrade. Okay, so I was in Canada for a long time. It's hard to get out of these metric units for me, in spite of being in US for the last 20 years, right? So sorry about that, but you can see here, very high strength you have in FRP, CFRP. But with the increase in temperature, resin is intact, it gets decomposed, it completely evaporates. You can see here the phases it goes through. And you need, for fire design, for those of you who don't know, you need stable properties. That's what we have in concrete, up to 800 degrees centigrade if you want fire resistance without any supplementary fire protection. It's not 200 or 300. Then you need some supplementary fire protection, right? So, then similarly we did bond tests. As you can see, bond degrades much more rapidly. This is the bond strength with temperature. Even after 80 degrees, you start to lose bond significantly. And by 200, 250, it's almost completely, though you have the tensile strength in the fiber still intact, that doesn't help too much, right? Maybe through anchorages and stuff it will help. This is the bond slip at the bottom, bond modulus, I'm sorry. So, we also did, as I said, the problem with FRPs is different types, different GFRP materials, So, all this is a problem. So, we did this for Canadian PWJC Public Works. They used in the Canadian Parliament building slabs with GFRP. So, at that time, we did for we compared here, this is the normalized strength 100% at room temperature versus temperature. As you can see, this is the steel radius. So, you have at 550 degrees centigrade, steel loses about 50% of its strength. That's very helpful for defining failure in steel. That's called the critical temperature. Look here, this is GFRP, the squares, and this is CFRP, two diameters. So, GFRP at 325 degrees, it loses 50% as compared to 550 in steel. CFRP loses at 250 degrees. Right? So, I think this indicates that they lose strength quickly. Now, we tested number of structural members, including columns, and we experimented with NSM, internally reinforced, different members, as well as with externally bonded attached to the beams as well. Beams I just showed you here. Now, just quickly to show if there is a column here, it's strengthened with FRP. This is all supported by industry, so not much money comes in, so they don't want failure. So, quickly we put the insulation as well to make sure it lasts for 3 hours and 4 hours, especially in this project what we did. So, if you see here, this is the fire curve. This is what we have to satisfy, as Steve showed in ASTM E119. And this is, we put in insulation. This is the insulation temperatures at the edge of the insulation. As you can see, this is in minutes. And this is FRP temperature. As long as you keep the FRP temperatures cool, no problem through the insulation. You can get 4 hours in this case for a column, huge column. The column which was tested was 16 inches square or circular. Now, as soon as this is where the glass transition temperature is reached in this. After that, you can see the temperature starts to go up, right? And the beams, the column starts to deflect. As you can see, this is with 1.5 inch thick insulation. This column, it first expands and then contracts and slides, and then these are with 2-inch insulation, the columns. That's the deflection, axial deflection. Now, you have then beams. What about beams? As you can see here, we tested number of beams. I'm going to show you quickly some results from the most recent test. This is the beams with near surface mounted reinforcement, where you insert strips into the beams for repair or strengthening applications. Okay? And we tested this at Michigan State University. What happens? First thing, we want to experiment without any insulation. Whether we putting insulation, it may not be expensive, but when you include labor and stuff, it adds, as well as a lot of times you don't have enough headroom, right? In applications and stuff, that becomes an issue as well. So without insulation, these are NSM strips. We increase the capacity by 40%, right? So by putting those strips, and here we use insulation. If you don't put insulation, in 10 minutes, in spite of having some concrete cover, about 20 millimeter, it starts to, ignition happens, epoxy starts to burn. And in 25 minutes, it starts to flake. And at 80 minutes, the cracks you can see wide open in the observations through that. But if you put insulation, about 25 millimeters insulation thickness, we used vermiculite gypsum combination insulation, 35 minutes, no issue here as opposed to 10 minutes, 60 minutes as opposed to 25 minutes. So it lasts longer as well. It's not just the duration, but it's this thing as well. I don't have much time, but you can see here that this is the temperature in the steel rebar. In the case when you use it for strengthening applications, EB and NSM, the steel rebars are very important. It's not just your this thing, because in case if something happens, they have to continue to carry the load if FRP cannot carry the load. So these steel temperatures, keeping them cool, this is the steel temperature in the insulated beam. This is without insulation. So this is bad. That can lead to early failure. In FRP itself, you know that NSM FRP slots, as you can see, if you don't insulate, they quickly rise the temperature. They don't have anything to contribute after 15-20 minutes into the fire. Right? So then same thing, deflections. This is externally bonded. This is a conventional reinforced concrete beam. When you strengthen it with outside FRP like this with insulation, this is how it behaves. This is the deflection in the beam. And these are NSM. So NSM is possible to get required fire resistance without any insulation up to 2 hours. It's easily possible. But EB, when you put it just outside, it's almost impossible to get more than an hour. It's more than an hour. You always need some kind of an external insulation. Okay? So these are some of the pictures of BAM. Let me skip it. So this is what happens. This is what Steve was talking about. This is in the anchorages. You know, if you keep them cool, they try to hold this together and they act like cable basically. Through that mechanism, it continues to carry a little bit of load. Through the fibers are not intact anymore, but they are separate, each one of them, right? So now we develop numerical models. So I would, if you want more details, go into some journal paper and find a number of journal papers are there. That's not the main point here. But when you want to model this, it is concrete structures itself is hard to model, especially under fire because of spalling and other things. Additional complexities such as bond slip relations has to be incorporated very much. These anchorages have to be properly accounted for. It gets extremely complex. So it's hard to do it in a design office. So we modeled this through finite element modeling. We developed our own models and then varied lot of parameters to see what parameters influences so that we can engineer the system for better design, right? Rather than just using some test data or one-point test data. So this is, for example, type of FRP strengthening. This is a concrete beam, or this is beam 1-1 reinforced concrete beam, just reinforced concrete beam. This is strengthened with NSM. This is EB, externally bonded here, and this is NSM. Can you see that there is NSM? So in each case, we increase the capacity about 40 to 50% with addition of EB or NSM. Now you can see here, in the case of the beam, reinforced concrete beam is like this because it's 250 kilonewton meters. So nothing happens up to 70-80 minutes in concrete as we expected. So then it starts to moment capacity. This is moment capacity. Now if you strengthen it with EB, within 15 minutes or so, glass transition temperature is reached, the strength degrades in FRP, and then it behaves just like a reinforced concrete beam. So the FRP is gone. Now if you add NSM, as you can see it here, though NSM temperatures are rising, but they are rising slowly, temperatures, and after glass transition temperature it drops, but still it continues to have some strength because of the protection it gets from the concrete cover thickness, right? Gradually it drops. Now if you see, for example, this one here, how to strategize even putting this NSM. If you want to use NSM as the reinforcement, this is not a good option to put NSM across, putting number of bars. If you can put it at, because the heat will be coming at the corners from both sides. So in a fire situation, corner bars will lose very quickly, right? So if you can put them closer to at the mid span, instead of 4 bars put to, that gives you additional 50 minutes at least. Additional fire resistance you can eliminate. When you need 90 minutes of fire rating, you may not need anything else rather than that. So, okay? So that's a better option. Now, what about how much you strengthen? A lot of times material cost is not that much. So what happens is, if you strengthen it, if the FRP more the FRP contributes as part of strengthening, worse it is from the fire point of view. So lesser the contribution of FRP, if it is 29.1% is the contribution of FRP in this case, it will last 135 minutes. But if the contribution of FRP is 40% plus, then it can fail in 80 minutes. So, unnecessarily don't strengthen it too much. Okay, you can take that measure. Then, what about bond? Bond is the major issue. It has to be accounted for. This is the response of moment capacity, how it drops with time. If you don't account for constitutive relations for bond, then if this is no fully slip happens, no slip happens, but it's somewhere in between. And that property depends on the type of the FRP, whether you're using your GFRP, CFRP, right? That needs special constitutive relations. And how much thickness you need. Remember, as I said, in these beams, when you want, once you have it, it's not the FRP only the thing you should look at. You should look at the steel rebars as well. So making steel rebars cooler or keeping them cooler is very much important. This is, for example, rebar temperature in the steel, for example. Higher the thickness you have, lower will be the rebar temperatures in steel as well. That will definitely help to carry more time. And how do you do that? I'll show you that. So you need to strategize how you provide this insulation, having said that. So when you use externally bonded FRP, right outside when you put it, for example, this is not a good option, just putting underneath the beam. No. You need to take it, and even CC providing to the level of the rebars is not good. You need to take it 2 times CC, 2 times the concrete cover thickness to get the full benefit. Or you can take it fully, but you are wasting your time. You don't have to worry about that. You are wasting material and stuff. So 2 times the concrete cover thickness is the most optimum. We experimented it with test models. Same thing for T-beams as well. How much you need? With EB, if you need 2 hours of fire resistance, you need 20 millimeters of insulation. If you need 3 hours, 4 hours, but you make sure you extend it on the sides as well. Okay, at 2 cc, 2 times the concrete cover thickness as per ACI 318. Now, what about NSM? NSM, you can get away without fire resistance sometimes, and most of the time up to 2 hours, if provided you place the bars only at the center, not at the edge, not at the corners, right? And how much insulation is, this is the most effective way. Again, 2 times the concrete cover thickness, just like before. And how much you need? It's given here, very much similar. You need certain cover thickness to get 2 hours, 3 hours, 4 hours. You can achieve that. Now, columns, similarly, columns. Up to 2 hours, it's possible if you properly design your columns with loads and stuff like that. But beyond 3 hours, it's impossible to get. You need some level of insulation. Structural Technologies have a very effective insulation, as well as 5 company formerly has developed VGEI coatings. So you can use this kind of an insulation to get your required fire ratings. We also developed simplified design approaches that can be used in ACI 440 and other documents. It is basically based on heat transfer principles. You calculate the temperatures inside any section. Then apply structural mechanics principles to carry out your equilibrium equations, making sure all the forces are there. And then find out, this has to be done in different time steps. At each time steps, check whether the moment capacity it has is enough to carry that. If it is not, that's fine. So you can keep trial and error approach, but you need material properties. So I will just explain you this slide, one more slide left after this. If you see this is the beam. It is, let's assume you are using externally bonded, internally reinforced, near surface, anything you want. Now if you apply these methods, what's the best part? This is the moment on the y-axis for the beam, moment capacity. And the x-axis is at different fire exposure times. So if you do the calculations, let's say you have a concrete beam, this is a concrete beam which is not strengthened or anything, regular concrete beam. And this concrete beam, this is how it behaves. Nothing happens for 60 minutes, then it starts to lose. Remember, it has to carry lower service loads because, right? So because of that, your concrete beam fails here. Because the load levels is 50% of the capacity approximately, service load. So it fails right here. But if you strengthen with EB, you increase the capacity 1.5 times. So then it starts to, one day there is a fire here, then it starts to decrease. So because your glass transition temperature is reached, then it starts to behave just like a concrete beam, but it fails here because it's carrying higher surface. Now, if you put in NSM, look at this here. Why? Because NSM, because of the cover thickness you provided, the temperatures increase slowly in NSM. So it retains more strength. So it fails somewhere here. But if you insulate the same EB, which failed here, you can push it to wherever you want depending on the insulation thickness and its properties. So this is how the fire behavior of these beams are. So finally, there are it can be addressed. This is not a big science or anything. A fire problem can be easily addressed, but needs a lot of material level data as well as some validation test data which are expensive under fire exposure. Now, FRP up to 200 to 250 degrees centigrade is no big deal. You can manage. But beyond that, it loses much faster, rapidly the strength as opposed to steel, where up to 400 not much issues. Now, reaching TG does not mean it's failure, which some ports say that after TG, if it is reached, then neglected. It's not. Still, it's contributing to some extent. Okay, so that is where the calculations are very important. Now, simple modifications such as adjusting the reinforcement ratio, I told you how much to strengthen or where to place the bars. These strategies can help to get across the borderline without insulation sometimes. Okay, and a lot of further research is needed, and I would like to thank Next, for example. We are doing a project for them, developing. People are doing tests, but not paying attention to all the nitty-gritties of the test. Otherwise, the tests after $30,000, you don't know how to condition the specimen, what instrumentation has to be done, what failure criteria has to be applied. It's not in ASTM. It's not in ISO. So that's where we are focusing currently on one of the projects. So finally, I would like to thank many people, including the sponsors. This is about $5 million plus projects we did over the years. Mark Green is here, PCA, CTL, so many Argon-X right now, Structural Technologies, 5 company. So, and there is very limited information and details how to do these calculations. There are no books, as you know. We have a new book with a chapter of about 40 pages published by McGraw-Hill in this book for FRP design, what to be done. Okay? Thank you very much.